Thank you so much for watching the latest AI Weekly update on Henry AI Labs up to the day of June 30th, 2021. We'll start off with the latest on vision transformers, which continue to boom in interest as they're developing out the transformer architecture for computer vision applications. We'll start off with how to train your VIT, looking at pre-training, transfer learning, deployment costs, open sourcing 50,000 pre-trained vision transformer models, and studying things like the impact of data augmentation and regularization like dropout or stochastic depth regularization. Then we'll look at VIMPAC, video pre-training via mass token prediction and contrastive learning. This is a really exciting idea of using the vector quantized variational autoencoder to compress the video data and then simultaneously do the self-supervised language modeling task that has been really useful for natural language processing and one-dimensional sequences of data, which is also kind of analogous to the temporal axis of video data, as well as contrastive learning, which has been really useful for the two-dimensional aspect of the image learning in this video representation learning task. And then we'll look at EsViT. Similar to VIMPAC, it's exploring a new self-supervised learning technique for training these vision transformers. So inspired by the Dino paper from Facebook AI, where they have this knowledge distillation strategy and they compress the representations, max pool them, and then or mean pool them, and then compare these representations. EsViT is going to use this patch level representation. So they call this kind of an isotropic architecture where it has it doesn't compress the features in the intermediate neural network that much, and it retains the shape throughout the beginning to the end. So you would say that it has a representation for each of the original patches in the vision transformer architecture, which we'll look at the animation later to get a better sense of this idea. But they use this kind of merging of these patches and then have the distillation loss align the representations on these patches to help with this self-supervised representation learning task. Then we'll look at TokenLearner. TokenLearner is like a compression technique for these intermediate patches, which I think flows nicely with the EsViT architecture and understanding how we can compress, merge these patch representations for building more efficient vision transformer designs. And notably, the EsViT has like a 22 million parameter vision transformer that performs well. So it's not like you need massive computational resources to play around with these models. And then we'll look at FitVid. FitVid is showing that the variational inference thing for video modeling, as well as this design of having the conditioning and with the LSTMs and this dynamics architecture, actually can overfit these videos pretty well. So fitting these videos of like robots picking and placing things or sorting objects or whatever, it's not really a problem of you can overfit the video data. And then they show how you can use some data augmentation to remedy the overfitting, but overall showing that it's not a problem of model capacity. And also they show their architecture. You don't need to make it like a billion parameters to do this, just their variational inference strategy with this amortized inference, training, all this kind of idea. You can overfit video without massive models. Next up is my favorite paper from this week, Co-Advised Cross-Inductive Bias Distillation. I really like this idea of combining these different architectural biases, like the difference between, particularly in this paper, the convolution and the involution, and using those two different models to distill it into a transformer. So what they show that's really impressive is that, or really interesting, is that as you keep training the ResNet convolutional networks, the student model doesn't actually improve as the teacher continues to improve because it already has learned this inductive bias. But if you share it between having two distillation tokens between the convolution model and the involution model, and the involution model is just that it shares the parameters across the channel axis. So whereas the convolution has that, say, 3x3 kernel of weights that is shared across the spatial height width of each feature plane, the involution is going to do that across the channel. So just a slightly different, or exactly opposite, different way of processing these feature maps with the convolution compared to the involution. They're going to distill these two priors into a transformer neural network, which I think is a really interesting idea with this diversity of functional diversity, ensembling, distillation, these kinds of ideas. I've been exploring corruption robustness is using datasets like ImageNet-C or the stylized ImageNet, where they explored that shape bias tendency thing. And they're looking at the transformer convolutional networks and showing where they degenerate on these kind of out of distribution test sets, trying to explore exactly where they fail in particular areas that they fail, like say you transfer the style of the images and then you show that it's only looking at texture and not the actual shape of the objects. This has been a really exciting week for deep learning with code data. Every week in the weekly update, I've tried to get at least one of these papers, last week being Break It, Fix It, where they're showing how these transformers can fix Python code with errors in it with this kind of generative modeling technique. This week, OpenAI and GitHub, they've announced this Copilot thing. I'm not going to go deep into this in this video. I'll cover that next week. But here's this is just something to obviously note that this has made a huge impact in media attention. And then this is the latest paper that we'll cover in this video, Code to Comma Translation, a comparative study on model effectiveness, and I don't remember that E word, but maybe efficiency. But so code to common translation, it's looking at, you have some code and then you want to generate a natural language description of the code. So like, code documentation. And they're looking at, particularly when you take like a BART model off the shelf, what are kind of the failure modes of this when you apply it to, say, Java data, generating natural language descriptions of code data. So overall, this OpenAI GitHub Copilot thing, it seems like a very ambitious application, but a lot of these papers, like most notably still is the apps measuring code competence with apps, showing that you can input natural language prompts and generate code using models like GPT-Neo and all these generative text models. So next up is the domain of deep learning with tabular data, and this is where we have, say, like these CSV files with heterogeneous features that describe these rows, or say like individual customers, or whatever it is that we're describing with tabular data. So it's common that say XGBoost, these gradient boosted decision tree models, perform better than neural networks. We have two recent papers that are showing that neural networks can outperform XGBoost. The first being regularization is all you need. They have a massive configuration of data augmentation, regularization, and doing a hyperparameter search through that shows how to improve the performance of a neural network and have it perform better than XGBoost. And then revisiting deep learning for revisiting deep learning for tabular data looks at these all these latest architectures for repurposing deep learning, so it has this different kind of feature fusion for this particular kind of data, and then designing a new kind of transformer to handle this data. So then in the field of natural language processing, one of the most exciting applications of deep learning, we have the best sentence embedding model ever. This is a community organization effort from a researcher at Hugging Face that is developing something like, they have, I think it's something like 215 million pairs for contrastive learning, or positive pairs for contrastive learning so far. And we'll get into this this content later as they describe all the different ways they source these positive pairs. But the effort seems to be a big contrastive learning training effort for these sentence BERT Siamese encoding models that can do sentence similarity and this kind of thing. A really exciting effort on training these sentence embedding models, and say having the latest edition of the sentence BERT models in the Hugging Face Model Hub. Next up is Charformer, where you're taking individual characters and using those as tokens. So the problem with that is obviously to have a really long sequence length if you treated each character like it was a token and don't use things like byte pair encoding, subword tokenization, and that kind of thing. So they're designing this algorithm that uses 1 gram, 2 gram, 3 gram, 4 grams, and then has this attention over the representations over each of the things, pulls them together in this interesting strategy of tokenization end to end instead of having this pre-processing step and learning how to tokenize data. DocFormer is an interesting kind of thing. I didn't really get into the details of it, but this visual document understanding. So I don't know how many weekly update episodes it was ago, but the Allen Institute has released this architecture called GPV, General Purpose Vision. These ideas of combining language and text, these kind of architectures. This is a strategy of this multimodal attention over images and text, and then applied to this problem of visual document understanding, which I think is really interesting. Because say when we have these research papers that we're trying to process, we include these figures and things to communicate the results or demonstrate the algorithm. So I think it's really interesting to combine vision language processing for document understanding. And then BARTScore, which is a really interesting paper, similar to when they're trying to evaluate the image quality of, say, generative adversarial networks. One paper was classification accuracy score, where you try to see how well you can train a classifier based on the generated images from a GAN or VQVAE or whatever it is. So BARTScore is kind of like that. You're trying to evaluate generated text by seeing how well that generated text can be used for downstream applications. So say you produce a summary and then you have like a natural language inference task from that summary. So an interesting idea for evaluating generated text. So next up in the space of knowledge distillation, we've already seen a previous paper on knowledge distillation, co-advised, cross-inductive bias distillation. This is simple distillation baselines, looking at further into the difference between online and offline distillation. I recently made a video on knowledge distillation, a good teacher is patient and consistent. That's also taking this idea part of having, say, a fixed teacher for distillation, where you can pre-compute the activations and then you don't even need the teacher model for the distillation training loop, compared to keeping it and then having the same kind of data augmentation procedure go to the teacher and the student. This is further looking at this difference between online and offline baselines in this short paper that's showing these results. So then in the domain of understanding deep learning, or the advancement of deep learning very generally, we have distributed deep learning and open collaboration. So this is where you use this volunteer computing approach to try to train the SWAV clustering algorithm and the Albert language model. So they describe these different ways that they say use synchronous data communication by having large batches to say, deal with slower computers, and then other ideas about the all reduce these distributed training algorithms that they're modifying so they can work with less bandwidth and then have a community of computers compared to like one centralized distributed system. So then randomness and neural network training, characterizing the impact of tooling, is looking at this kind of deterministic output where you say you want this algorithm produces 83.5% accuracy, and deterministically every single time you run the algorithm it produces its accuracy. But there are different sources of randomness, like the stochastic data augmentation, random splits of the like shuffles, like orders of the data, and other things they document in the paper, like say you have some kind of random layer in the model as well, or something like that. So they're taking apart the impact of these different these randomness, the randomness in these algorithms, like SGD, all that kind of stuff, and then crossing that with different hardware, so different like GPU designs and this kind of thing. And similar to the paper, What Do Compressed Neural Networks Forget? They show, and also self-damaging contrastive learning that builds on that idea. They're showing that it's the long tail, certain classes, subgroups are forgotten with this randomness. So it's overall, if you look at the top 1% accuracy, you don't really see the problem. But if you drill into the class imbalance metrics, interclass metrics, then you'll see the problem with this randomness across different kinds of hardware. So then lossy compression for lossless prediction. This is an interesting idea about using data augmentation to only compress the most salient information from data. So they motivate this with, say, climate science, satellite images, or I don't know exactly what images, but with climate science, and then self-driving cars, where they have these massive image data sets, and they don't really need to store the images. So ideas like compress it with an autoencoder, and then exactly, what do you need to compress? What's the minimum description? These kind of information theory ideas. So they're showing this idea with this data augmentation. I haven't really drilled into the details of it, but this idea of using data augmentation to only store the most salient information for compressing these large data sets. So next up, if you thought the animation of the StyleGAN2 latent space was impressive, this alias-free GANs is like outright scary how well they can animate these faces by traversing in the latent space through the latest modifications. And they show another one of these tables where they show how the FID score is decreasing from StyleGAN2 to alias-free GANs with these different modifications. And I'm not going to go through the technical details, just kind of looking through the animations and the high-level results of this latest design for these super photorealistic generated images with GANs. Then AdaMatch has been added to Keras code examples. So we'll walk through this implementation from Sayak Paul. Then some kind of meta information, the Hugging Face version 4.8, making it easier to push models to the model hub. Hugging Face dataset streaming mode, so you don't need to wait for the dataset to load, which can be really useful for, say, language modeling or anything with big datasets. On the usefulness of the Netflix prize, kind of an interesting anecdote about this $1 million Netflix prize in 2006 that I think everyone's familiar with, and kind of how that led to the evolution of, say, Kaggle, and debunking the myth about that it was never really useful, that the competition wasn't really useful because the winning solution was this massive ensemble compared to where they actually did have a solution from it that they implemented and was productive. And then Andrej Karpathy talking about how Tesla is using their computer vision system at the CVPR conference. A really interesting and exciting talk that I highly recommend watching. Amazing things like their data engine discussing having 6 billion annotated images with these objects, and the problem of depth, getting rid of radar sensors. Overall, really exciting talk about self-driving cars. That concludes this preview for this AI Weekly update on the week of June 30th, 2021. Following will be a deeper dive into each of these things. The content links for each of the papers or blog posts or whatever it is linked in the description of the video, and there are chapters if you want to skip ahead to something that will be covered later in the video. It'll generally be covered sequentially as listed on this Notion page. First up, we have how to train your vision transformer, data augmentation and regularization vision transformers. So as stated at the end of the title, this is a large-scale comprehensive study about the relationship between the amount of training data, augmentation regularization, model size, and compute budget, studied across both pre-training as well as transfer learning or fine-tuning. So one interesting study is that they're able to retain the performance between having much more data with strong augmentation regularization. So this plot is showing that you achieve about the same performance with 13 million ImageNet data, 13 million samples from the ImageNet dataset compared to 1.28 million with strong augmentation regularization. And they're showing this continues across increasing scales from 13 to 300 million, as stated in the title, that they're able to train a VIT model to achieve the same performance with the about 13, 14 million images in ImageNet 21K, compared with JFT 300 million, that kind of exclusive data set to Google. So probably more interestingly for most of us is the transfer learning performance. So what they're showing here is that it's definitely better to do transfer learning compared to training a model from scratch with a smaller data set, like the PETS 37, where they have 3,000 images, or this other data set where they have 30,000 images. And these are data sets from the Visual Task Adaptation Benchmark that's studying the behavior of transfer learning, where you have these large pre-trained models from, say, Google or the Hugging Face Model Hub, and then you're transferring it for your given task. So they have a lot of interesting findings from this study. You can see the different configurations of the VAT models they train, as well as convolution, transformer, hybrid models. And these are the configurations of regularization and data augmentation that they explore in their study: dropout, stochastic depth, different magnitude parameters for different settings of data augmentation, and then weight decay. So one of the interesting things from this paper is the relationship between data augmentation and regularization. But first, quickly before we get to that, this is another plot showing the difference between transfer learning and then training from scratch. So you see the difference between transfer learning, the compute required to achieve reasonable performance on PET 37 or this other data set, and that compared to training from scratch. So better to do transfer learning. And they also have open sourced 50,000 models, as they show, which is a massive amount of open source models to have trained in open source. And they think that you could do some further research on model analysis using this source of 50,000 open sourced pre-trained vision transformer models. But here's an interesting result from the end, comparing data augmentation and regularization. So they show that in some cases, regularization, shown on the right is regularization, and then the left is no regularization, and then data augmentation going from left to right, rightmost being the most data augmentation. So what they're showing here is that regularization can hurt performance compared to where data augmentation generally performs better. And kind of my interpretation of this is I think data augmentation is more than regularization. I think data augmentation kind of has like a causal mechanism to it. It's doing this invariant encoding. I really think data augmentation does more than just regularization and preventing overfitting and that kind of idea. In the scope of how to train vision transformers, we also have some new strategies emerging for how to do self-supervised representation learning with these vision transformers, and overall the scope of self-supervised learning for computer vision. So this paper, VIMPAC, Video Pre-Training via Mass Token Prediction and Contrastive Learning, is using the visual tokens generated from a vector quantized variational autoencoder to facilitate this task of video representation learning. So video data is massive. It has, say, 30 frames per second, and these can be high resolution frames. So having some kind of way to compress the data using these vector quantized variational autoencoder tokens, which is a strategy of compressing data into this Z bottleneck. There's the variational inference thing where you structure the prior of the distribution of Z and all that stuff, and then the discrete part is just about having a discrete codebook rather than a continuous latent space for these encodings, but none of that is really particularly important for this study. They use a pre-trained vector quantized variational autoencoder. It's not a part of the training of the algorithm. So first they take the frames, they compress each individual frame, describing in the paper how it's better to compress each frame than, say, have like a video compression model that tries to encode all of this with, say, like the time-S form architecture, which is what they use in the study. But so you take it and you compress each individual frame, and then you're going to do this contiguous block masking where, similar to SpanBERT, you don't just mask IID. You're going to take a whole region where you sample from these coordinates on the temporal axis, height, width, and that forms the contiguous block that you're going to mask out and then reconstruct. So it does these two tasks of reconstructing the mass token prediction as well as contrastive learning. And they're showing, interestingly, that this strategy with the compression is able to do contrastive learning with very distant frames. So they describe how they do something like 400 seconds ahead. I think it's in their contribution list, so they describe how they're able to do 400 seconds away compared to previous work that, say, uses contrastive learning for video representation learning, where two frames from the same video are positive pairs, and then frames from other clips and other videos in the mini batch are the negative pairs. So say you have like the UCF 101 data set where you have a video of somebody cooking something and then a video of somebody kicking a soccer ball. The soccer ball frames would be like the negative examples. Two distant frames from the cooking video are the positive pair. So they're able to do much longer range contrastive learning. And overall, they show how this is a competitive approach with other state-of-the-art models on video recognition, particularly on temporal heavy data sets. So they describe how these spatially heavy data sets like UCF 101, HMDB 51, and so on, you could classify these actions from a single frame, whereas these actually require the temporal long-range modeling. So a very interesting idea of combining these self-supervised learning algorithms for video representation learning. Along that vein, here's another strategy for self-supervised learning with vision transformers for computer vision. And also just to note, last week we looked at the BEIT, BERT pre-training of image transformers. This is also using these vector quantized variational autoencoders to form these visual tokens. And then when you have the patching, this is the vision transformer takes images and chunks it up into patches and then has this attention across the patches. So you're going to mask out the patches and then try to align the masked out patches with the visual tokens from the discrete vector quantized variational autoencoder codebook. But just to show, this is another strategy. There's been a lot of recent research about designing new self-supervised learning tasks for these vision transformers that are performing better than I imagined with ResNets, or they haven't really been tried. You see how they have this kind of BERT style architecture where you're indexing it on this BERT style output, and we'll see another paper later in the video. Co-advise is also using indexing these different things, like where you had the CLS index the separator token. This kind of ideas of using like this BERT architecture that seems to be really good at multitask self-supervised learning, where they combine these different tasks for learning. But anyway, so here's another paper that's a new strategy for self-supervised learning. But so this new content, EsViT. Really interesting results on improving efficiency as well, as which they'll show later in the video. So here's the idea from the paper. So they're using this idea of distillation between teacher and the student, where in the Dino paper you pool upon the representation for the entire image and then compare this pooled representation on the CLS token, again with this BERT style. They call this like isotropic, meaning that it doesn't compress the feature maps. It holds the same dimensionality of the sequence length throughout the model. But now what they're introducing is patch merging. Patch merging is the big new idea in this paper. So patch merging is saying, all right, first you take the image, you chunk it up into these 14 by 14 or whatever patches, and then iteratively throughout the model, you're going to merge the patches through this like 2 by 2, max pooling operation, where you gradually eventually have a representation for the whole image. So that's the idea of the multi-stage pooling these representations. And then the idea from Dino, the self-supervised learning paper, is so instead of just matching the pooled representation with the teacher, you're going to also match these individual patch encodings. So these can be thought of as the representation. This can be thought of as the representation for this, fourth of the image. So you'd align this between the teacher and student as well. And they show how this new region-level pre-training strategy is going to improve over, previous state-of-the-arts using this efficient model, or I might have been wrong about exactly how small the model is, but I think it's an efficient new model that doesn't need a massive amount of parameters to perform well, and probably because of this spatial pooling aggregation of the patch embeddings. Similar to the multi-stage aggregation of these patch embeddings, where we're looking to compress our representations, and more so in the multi-stage setting, we're looking to have this global representation as we're attending over all the patch tokens. What we're looking at here in TokenLearner, what can 8 learn tokens do for images and videos, is having this massive compression bottleneck at the beginning of the image or video data. So tokens, say you had a character sequence length, and later in the video we'll look at the Charformer architecture. That would be encoding all of these characters individually. So Charformer turns into CHARFORMER, compared to the tokenizers where you block it up into char and then former, say, being 2 separate tokens. It's this huge compression bottleneck in the beginning of the network that performs very well for these natural language processing tasks. So they're looking at having this huge compression bottleneck with these input representations of, say, 224 by 224 by RGB image compressed into these learned tokens with this spatial attention operation that transforms us into these visual tokens, as they call it. So they have this huge bottleneck in the beginning of the layer, the model, and then that's how they have this different architectural components. But that's the idea of having this huge compression bottleneck in the network that helps with efficiency. Next up, we have FitVid, overfitting and pixel level video prediction. So I don't know too much about this research, but what they're doing is they're showing that you actually do have the model capacity for predicting future frames in video data. So say you have robot data where it has a visual sensor, and these are the visual video frames of learning to, say, like pick up this object and put it in a bucket or something. And they're showing that this architecture where they have this encoding of the image frames, dynamics, introduction with the previous hidden state and the action that's been taken, using these LSTM encoders, and then going into the future, and then say having the variational autoencoder, this kind of variational inference bottleneck where you have this likelihood, all this kind of stuff from the variational autoencoder that's used to train these predictions of future frames, and you have this so you can have different continuations of outputs and structure the latent space of doing this kind of modeling. But what is interesting is that they're showing that you actually can overfit to this without just scaling up the number of parameters. They provide a link if you want to see examples of the videos that they generate using this model, and overall really interesting to see the continuation of video generation and this kind of efficacy of the variational autoencoders. We now have a few different neural network architectures for computer vision tasks, like the convolution where you share the weights across a spatial kernel, the involution where you share the weights across a channel kernel, and then we have the attention layer in the transformers, and we also have, say, the fully connected multi-layer perceptron layer. So what this paper is doing, co-advised cross-inductive bias distillation, is looking at trying to merge this function diversity into a single architecture, the vision transformers, through knowledge distillation. So what they're doing is we have the convolution, involution, and then the transformer, and they're showing that these different inductive biases, although they're trained on the same data, they learn different things about the data because of their inductive biases and the functional diversity. So they introduced this strategy for, this is a visual diagram of the convolution. It shares these weights across the channel, and the involution goes across the height-width plane, and then this goes across the channel, the difference between convolution and involution, that they're distilling into the transformer model. So the transformer model, in the similar kind of BERT style of doing multitask learning, you index the CLS token to learn from the cross-entropy one-hot encoded labels, and then you learn from the soft labels from the convolution and the soft labels from the involution model. This is like the red net and compared to the res net, and you index these different tokens to apply this knowledge distillation loss, and you have these special tokens on the input, which is how you process the input data to pass it into this architecture. So in the end, they show these interesting results where they improve the performance. Probably the most interesting table is this one, where they show that even though you continue to improve the teacher model, so going left to right, you're going epoch 50, epoch 100, epoch 150 with the RegNet CNN model, but even though the teacher is improving, as you see going left to right, the student isn't really improving. And then they show a similar thing with these with the parameter increases. So this is training more compute, training more epoch steps, and this is increasing the number of parameters in the teacher model. So even though the teacher models continue to get better, going from 200 to 600 million parameters, it doesn't matter for the distillation into the student model. So overall, they show how this, distilling the CNN and the involution network does improve performance. And overall, I think it's a really exciting idea for knowledge distillation and taking advantage of these the functional diversity, maybe combining it with neural architecture search or other kinds of ideas for exploring the space of inductive biases in architectures and how this leads to learning different things about data. In a similar vein is trying to distill the different inductive biases introduced by this architecture design in the co-advised paper. This paper, Exploring Corruption Robustness, Inductive Biases in Vision Transformers and MLP Mixers, is looking to drill into the failure modes of these different architecture designs. So the data sets that it's using are ImageNet C and then TextureQ conflict. So these are two strategies of producing this corrupted data. So say you use data augmentations like Gaussian blurring or like a weather style transfer, just adding noise, or these other kinds of style transfers of the images to try to produce these special corruption sets, and then compare the performance with the vision transformer and then the MLP mixer and the CNN to see how they perform differently on these kind of models. So, overall, here are the results from it, and I don't think they have any big conclusion that says, we really found this profound difference between these different architectures, but overall, these kinds of studies should help with understanding these biases. Deep learning with code data is one of the most exciting topics recently, especially with the latest announcement from OpenAI on this Copilot thing that looks like you can put in a natural language prompt and then generate any kind of code. We saw measuring coding competence with the apps challenge that shows that you can solve these interview style challenging data structures problems by just inputting a natural language description of the task. So here's the latest paper on this that I thought was interesting: Code to Comment Translation, a comparative study on model effectiveness and error. So these generative models, whether it's style GAN generating images or, these BART models that generate text summarization or chatbots or whatever it is, it's hard to automatically evaluate these models. So we have these metrics like the Blue Score, Meteor, Rugel that, have these different things like, say, n-gram overlap between some annotated ground truth and these kind of strategies for evaluating generated text. But they're saying that this study, that let's have a qualitative look. Let's, take apart some of these generations and see what we can learn about how well these models summarize code. So they're studying the CodeBERT model, neural code sum, and code to sequence that is operating over this Java data set where you have 2.1 million Java methods with paired java.comments, and the authors are inspecting what is generated and what they can learn about the errors that are being made. So in the end, they provide this table of different kinds of errors: missing context, missing information, incorrect semantic information, and so on. And this might help understand, maybe you could, better curate data or use data augmentation or things that you can learn from, analyzing the failure modes manually to see what's happening with the text generation. Here's a quick look at two of the latest papers on applying deep learning to tabular data. Regularization is all you need. Simple neural nets can excel in tabular data, and revisiting deep learning models for tabular data. So what this one is showing is you have 40 tabular data sets, and you're doing a hyperparameter search across the regularization parameters, as they call the regularization cocktails for MLP. So what they're doing is they're looking through different ways of applying data augmentation, weight decay, say like stochastic weight averaging or dropout, these kind of strategies, as well as say like structural path dropout or like batch normalization. So they're looking through all these different regularization techniques and showing that as you search across it, you can get better performance. So this is the overall table of the hyperparameter sweep that they're about to go through, the different augmentation configurations and so on. And then they're showing that this can outperform XGBoost when you really search through these configurations across these different tabular data sets. And then revisiting deep learning models for tabular data is looking at these customized architectures that have been designed, say repurposing like convolutions or attention layers, and then designing a new model. So SNN, Node, TabNet, GrowNet, these are some of the neural network designs customized for tabular data. And they end their paper by designing their FT transformer feature tokenizers to say this is like the CSV, like the Titanic data set where you have like the gender, the passenger class, or like where on the cabin, these kind of tabular data records, and then having some kind of feature tokenizer, and then applying this with the transformer architecture. So overall, I think these are just two interesting papers. I don't know too much about this space, but this space of applying deep learning to tabular data, and something that you commonly see is deep learning not for all data and so on. And even with this, I'd imagine that maybe how much data you have matters as well. But again, I haven't really taken apart these papers that much. A new campaign has been launched to train the best sentence embedding model ever with 1 billion training pairs. So what this is talking about is using models like the Siamese sentence BERT to encode sentences, and then you have these representations they can use for like similarity analysis, like duplicate detection, or just information retrieval, say query sentence matching, and so on. So the quality of sentence embedding models can be easily increased via larger, more diverse training data and larger batch sizes. So describing the roadmap of creating this JAX training framework using the TPU v38 that has 128 gigabytes of memory to allow for, say large negatives in the contrastive learning batches, as well as this set of training data. So I think this is really interesting. So here's the listed data sets, the paraphrase data for forming the positive pairs. They have data from natural language inference, sentence compression, say it's like a rewritten sentence that's shorter and contains the semantics, and all these things. I haven't gone through all this, but this is a source of these different data sets for forming these positive pairs for alignment between these representations. So they're going to try to gather together a massive amount, say 100 million plus training pairs, and I assume that means positive pairs, they're using to train these models. So they're talking about some other ways maybe they can find some more data to reach a data set of 1+ billion pairs, and then train this to create the best sentence embedding model that ever existed. And then this is, from Hugging Face, we imagine that we'll see these models on the Model Hub, and this could lead to a huge advancement in information retrieval applications, as people can just grab this model from the Model Hub and use it for duplicate detection, nearest neighbor search, all this kind of stuff. If you're completely unfamiliar with this idea of dense text representations, like this idea of contrastive learning with these Siamese BERT, sentence BERT models, Nils Reimers has also made a 3-part YouTube course explaining this concept that'll be linked in the description of this AI Weekly Update video as well. Another exciting development in natural language processing, which may be essential for applications like deep learning with code data as well, or any kind of covering this, say, multilingual, this large distribution of word tokens, is learning tokenizers end to end. So rather than having this preprocessing step of subword byte pair encoding that is used to chunk this text into tokens, learning the tokenization end to end with gradients. So AI Coffee Break with Letitia, or otherwise known as Miss Coffee Bean, has made this really great animation that illustrates this concept of the Charformer fast character transformers via gradient-based subword tokenization. This video provides an animation that shows the algorithm of dividing these characters into 1 gram, 2 gram, 3 gram, 4 grams. You see the repeating of the n-grams, and then having this soft attention over each of these representations is used to pool them together into a single learned token embedding for the input character sequence, which could be a really exciting advancement in natural language processing. We've seen things like K9, a lot of different advances that I don't remember too well, but it's been maybe like a paper every 2 weeks, I think, on this idea of learning tokenization end to end. With a similar namespace, we have DocFormer, end-to-end transformer for document understanding. So I don't know too much about this research, but just quickly, I think this is really interesting to try to have this paired text and visual information understanding for processing, say, documents. So let's say you were, building some scientific paper mining system using these figures and this visual information of the, architecture diagram, how they arrange, say, the data is presented, how they show their self-supervised learning tasks, where they have a similar, again, this theme, I think, this week is looking at these BERT-style multitask learning, self-supervised learning things where you stack together all these different self-supervised learning tasks. And this BERT architecture seems to be really good at, not having conflicting gradients and these other kind of problems that, say, happen with self-supervised learning. But anyway, so this kind of visual information, encoding this alongside with the text, I think is a really interesting direction for future research on document understanding. Next up, we have BARTScore, evaluating generated text as text generation. So from what I understand, this is similar to, say, the classification accuracy score, where one strategy for evaluating how well generative models perform is to try to, say, train a classifier on the generated data. So in classification accuracy score, you use, say, the big GAN model or the VQ VAE to generate images, and then you fit a classifier on that, and then the performance on the real test set is how you evaluate the quality of the generated images. So it seems to me what's happening in BARTScore is you use these generated summaries in order to generate, say, a hypothesis. So they have the source data, and then they have the summary of the data, I think, and they use this to generate the hypothesis. They use it for ranking and regression, and more details if you really read the paper, but I haven't read too much about this, just a high-level overview of this kind of, this title caught my attention, evaluating generated text as text generation, an interesting solution to this problem of evaluating generative models without, say, like these, n-gram overlap scores and these miscellaneous kind of things. Next up, we have simple distillation baselines for improving small self-supervised models. The authors note that these latest techniques like MoCo, bootstrap your own latent, or seed these contrastive learning algorithms really only work for large-scale models compared to, say, the ResNet 18 model. So they're exploring these two different settings of knowledge distillation, offline and online, for using knowledge distillation to train these ResNet 18 models. The offline setting being you first train the teacher model with bootstrap your own latent, and then you distill those representations into the student network, whereas with the online setting, as the teacher is learning the BYOL loss, the student is also learning from those gradients in the distillation, as well as learning the BYOL loss itself. So two different ways of how you're structuring the curriculum of distilling this knowledge and transmitting these representations. So overall, look at combining distillation with bootstrap your own latent and then evaluating it on smaller scale models. Distributed deep learning and open collaborations is trying to get away from this problem of having to have a centralized data center for training these deep neural networks. And very interestingly, you have authors from Hugging Face working on this distributed deep learning and open collaborations project. So this requires, and they train Suave and Albert using this algorithm. So this requires taking apart some things of the distributed training algorithms to deal with, say, having more variance with compute speed, and then having variance with the bandwidth of these different devices. So this paradigm of volunteer computing, they describe how it's used in scientific computing a lot, and one of these strategies of designing these distributed systems. So first, they describe how they enforce training consistency by using large batches. So large batch training to avoid having like old gradient updates, these ideas of like distributed gradients, parameter servers, sending different chunks of data, these designs of distributed systems and so on. So they're describing these algorithms that they use to overcome bandwidth problems and so on, node failures. And they describe three different systems that they use to benchmark this algorithm, the server workstation hybrid, which have different levels of bandwidth configurations and how they train these different models. So I don't know too much about these distributed training algorithms, but overall really interesting to see this trend, and a very exciting trend to potentially see in Hugging Face. Earlier on, we looked at that paper that says, training the best sentence embedding model ever. Imagine that kind of model trained in this kind of distributed way with all that data and then put on a Hugging Face. It'd be a really exciting trend for deep learning. Randomness in neural network training, characterizing the impact of tooling, is exploring how the randomness in deep learning algorithms that prevents a deterministic output, deterministic meaning that the same thing happens every time you run it and that there isn't any kind of randomness in it. It's things like random initialization of the weights, data augmentation where you have stochastic sampling parameters, data shuffling, just like how you shuffle and batch the data, and then stochastic layers, like if you have dropout or different kinds of noisy, random sampling, like maybe what's used in StyleGAN, how you have this random sampling that you add to intermediate features and so on. This kind of randomness is introduced in these algorithms, and then how it varies across different hardware. So they explore different configurations of, say, different GPUs, P100 versus V100. And what they show is that although you can't really see this difference in the top one accuracy, similar to their paper, or I'm not sure how many of these authors are overlapping, but this paper titled "What Do Compressed Neural Networks Forget?" they show that it's the long tail, the class imbalanced minority examples that perform worse when you have this, randomness in the training. Lossy compression for lossless prediction is exploring how much of these images you really need to store when you're performing data compression for the sake of some downstream task like a supervised learning task. So they describe how some of these different applications have absolutely massive amounts of image data that they want to compress with techniques like the autoencoder or all these different algorithms for compressing image data. So they designed this algorithm, and I don't know too much of the details of this, but they describe an algorithm that has this kind of consistency with data augmentations in order to only save the salient information to compress this data. Next up, we have new changes to the StyleGAN2 model and alias-free GAN. So the StyleGAN2 model already was pretty impressive with generating photorealistic faces, but as you see in these animations, the beard isn't really super consistent, whereas this alias-free GAN is really crazy amazing how well this can transition between these generated images. So if you're interested in the details, you can look through the paper. It seems like there are some pretty technical details of how they're exactly changing StyleGAN2 to the alias-free GAN. But you can come to this website and see some of these animations that they're demonstrating and these really amazing transitions that will allow you to do animation in the latent space of these generative models. In the last AI Weekly update, we looked at the AdaMatch algorithm, and I've also made a paper summary video going through this paper, different ideas like distribution alignment and then the pseudo-labeling and this kind of fixed match build on. So here's an implementation by Sayak Paul and the Keras code examples of how to do semi-supervised learning and domain adaptation with AdaMatch. So this tutorial will walk you through how to go from MNIST into SVHN, this domain transfer idea, using this algorithm. So you have the processing of the data, you have the data augmentation that's used for this weak and strong augmentation, you have this consistency and all these different ideas that are in this flow of gradients in this AdaMatch pipeline. We have the source to the target. This is the idea of domain transfer. And then we have visualizations of the weak and strong augmentations. So here's the pipeline of AdaMatch. As a reminder, you have the weak and strong batches, this batch normalization thing. You have this distribution alignment between the logits of the unlabeled or the transfer domain and the class labels that are predicted, and this relative confidence threshold thing. So all these are implemented in these Keras code example. If you're curious about how any of this is really brought to life with Keras code, here's an example that does it. Transformers version 4.8 is out, now making it even easier to upload models to the Hugging Face Model Hub. As you see, trainer.push-to-hub, appending this to this trainer interface, which is how you fit the training data and use the batch size argument, all these different things for the Hugging Face Transformers library. So now it's easier than ever to train a model and then push it to this stored weight parameter server of the Model Hub. Also new in Hugging Face this week is the streaming mode for the dataset loader. So the Hugging Face has this datasets library, and now say instead of having to download some massive text dataset or whatever domain the dataset is, they're moving into Vision as well, you can now load a dataset in streaming mode, which is a really exciting feature of not having to wait to load all this data and having this kind of asynchronous pipeline. A really exciting advancement in the Hugging Face library. Here's an interesting blog post titled "On the Usefulness of the Netflix Prize," describing this Netflix prize where there was a competition to try to predict an algorithm that would produce an algorithm that would predict the 5-star rating that someone would give for a movie, given the user, the movie, the date, and then the rating as the training data with 100 million data points. And this famous competition to win $1 million by beating their Cinematch Netflix baseline system with this model. So this blog post describes these systems, this implemented system that was that was implemented with Netflix compared to this massive ensemble that wasn't useful because of the having 104 models. And then describing kind of the history of how this has led to like Kaggle competitions and the popularity of these kinds of data science competitions. So to kind of wrap up this video, I highly recommend watching this talk about the state of self-driving cars at Tesla from Andrej Karpathy. This is an amazing presentation about these different ideas like their data engine, the challenge of predicting depth, only using vision sensors and not using these LiDAR sensors, motivating the problem of self-driving cars, all these different things about really making this work with deep learning and doing this depth estimation, building this data set where they describe having, I think, like 6 billion of these images that they label. I don't know exactly where it's stated, but their data engine overall, very interesting talk. I highly recommend watching this.